Okay, thanks again. So today I'm going to talk about the hard edge of random matrix series. So these, is it okay? Oh, I thought I heard something. So these hard edge laws, they're really kind of the poor country cousin of the Tracy-Widom distributions. But I like them very much, and they actually encode the Tracy-Widom laws in a certain way, as I'll explain, and then for all beta, as the game has been. So to get at these things, you have to go back to these Vicious ensembles, or these sample covariance ensembles, or these Laguerre ensembles, whatever name you like, depending on where you come from. And we'll start with the complex Gaussian case. So I have n by m matrices M, capital M, all complex Gaussians, right? Mean 0, mean square 1. And then you look at MM transpose, or MM conjugate, whatever you call it. And you scale appropriately for the dimension getting large. You scale by a 1 on n now. Okay, this will make the spectrum order 1 as the dimension goes to infinity. And in this case, when you look at a global statistic, the Marchenko-Pasteur law replaces the semicircle. And to write something nice down, usually you specify a limiting aspect ratio. So we're going to do this as, the dimensions get large, both m and n get large. But we do this in a way such that m over n converges to some gamma. Let's take gamma bigger or equal to 1. It doesn't really matter. I mean, if you flip m and n, right, or take it less than 1, you just add some 0 eigenvalues. So you can, if you like, just take m bigger than n. So this thing is, so there's no 0 eigenvalues. So this is the statement. So the counting measure of eigenvalues, the empirical counting measure, converges in law to this object, all right? And so this is a little ugly to look at, right? The endpoints of support are these. The left endpoint is L, the right endpoint is R, and they're given explicitly in terms of this gamma, this aspect ratio. So it's better, I think, just to draw a qualitative picture. So when gamma is strictly bigger than 1, you have a blob like so. Not quite like so, but it's qualitative. The point is when gamma is bigger than 1, the spectrum pulls away from the origin. It doesn't see the origin at all. Right? But when gamma equals 1, equals 0, equals 1, then the left endpoint of support is 0. And you actually get an accumulation of eigenvalues at the origin. So this blows up like 1 over square root of lambda. Okay. So when gamma is bigger than 1, we already talked about how you would see Tracy-Widom fluctuations here. At this point, you again get square root vanishing, and it shouldn't be a surprise that you also get Tracy-Widom fluctuations there, F2 fluctuations at this point. Same thing here at the biggest point, right? But now if you want to look at the smallest eigenvalue here, clearly something else is going on, right? Because it feels the quote-unquote hard edge at the origin. So you get a different family of limit laws. So I just wrote this when gamma is bigger than 1, you have 2 soft edges or Tracy-Widom fluctuations. When gamma is 1, the left endpoint of support hits 0 and you feel the hard edge at the origin. So you get something else. In fact, if you take m to be n plus a for fixed a as n goes to infinity, you have a whole family of limit laws for the minimal eigenvalue. Okay? So at the global level, you just see that the matrix is asymptotically square, but at the local level, you actually see a deviation from square. Right? So for each a, you get a limit theorem for the smallest eigenvalue. All right, and this was actually also due to Tracy-Widom the year after their famous paper. Yeah?
It's obvious to get the Tracy-Widom in the case where it's the square root, or you have to...
Say this again? Like in this guy? In this case?
It's obvious to...
Yeah, I mean, the other case, it's very much the same, right? It's the local behavior at the edge. I mean, so what? It's the left edge. It still vanishes like square root, and the mantra is that should still be Tracy-Widom, and it is. Okay. This is no. Okay, so here's the deal. So in this case, right, I mean, in the bulk, eigenvalues should be 1 on n apart. Now you have all these eigenvalues pushing at the origin. You actually have to, blow up more to see something order 1. So the limit theorem is if you take, okay, again, in this picture, m minus n equals a, so there's a difference of dimension that's fixed. You blow up the minimal eigenvalue by n squared. This is in the beta equals 2 case. You ask for this to be bigger than some t. This converges to a Fredholm determinant in terms of the Bessel kernel. And this Bessel kernel, I write it here, J is the Bessel function of the first kind of parameter A. So in this way, this A appears, all right? And then of course, not of course, but I mean the real accomplishment in that Tracy-Widom paper is they found a Painlevé formula for this. I think it's Painlevé 5 or 3, but it's a Painlevé formula for the Fredholm determinant. Right? And of course, A appears as a parameter in that Painlevé expression. I wrote down here Painlevé 5, so
should be 3.
Should be 3?
I guess it should be. It's Bessel. No, it's Bessel. Okay.
That's very controversial. So it's 3 or 5. So okay, but here's so these laws. I mean, unlike Tracy-Widom that now appears all over the place, right? What we just call Tracy-Widom the Airy case. I mean, this is Tracy-Widom too. It doesn't get called something because it just doesn't show up. It doesn't seem to show up in all these kind of growth models that the soft edge laws do. On the other hand, if you go back to this picture and you think about after the fact, you push A to infinity, right? That should be like pushing the spectrum away. And if you can believe in exchange of limits, you should be in the soft edge regime. And that's indeed true. And what I mean by that is if you take the Bessel kernel and you rescale in the appropriate way, as A goes to infinity, you get back the Airy kernel. And that even holds at the Fredholm determinant level, meaning that there's appropriate rescaling of this limit law as A goes to infinity to the Tracy-Widom distribution in terms of Painlevé 2. So you can track this kind of hard to solve transition through the Painlevé expressions. So while these things don't seem to come up, right, they encode Tracy-Widom, right? They sit above it in some sort of hierarchy. So I think that's the real interest in these hard edge laws. And they're also more robust and easy to understand in the general beta setup. So that's what I want to introduce. I want to introduce an operator, random operator, that gives you all these hard edge laws, right? And then A will appear as a parameter, and so this will be a simpler family of random operators than the stochastic array. And after taking A to infinity, you'll get back stochastic array, right? So this will be a family of operators that encodes all the hard edge laws and all the soft edge laws for all beta. All right. So this made an appearance last lecture, right? There's a tri-diagonal matrix model for all the beta Laguerres, right? That's written in terms of a product of two random bidiagonals, and here it is. I've written it again, but kind of tuned for the hard edge. So here's the deal: you define a random bidiagonal matrix B. There's a scaling, and then on the first diagonal. The diagonal, there's only one diagonal, but the first off diagonal, upper off diagonal, you have a sequence of chi's that depend on the parameters n, a, and beta, right? The dimension, the difference of dimension in the beta. And here I put a minus sign on these chi's. This is something you can sneak in and it just makes things easier. All right? So I promise you that if you write down this matrix model, and now you can take any a bigger than -1, right? Now you can let this be a, not just be integer, right? But any parameter bigger than -1. And any beta, that if you look at BB transpose, BB conjugate, then the joint eigenvalue density of this W will be this disgusting looking object, right? And as before, when beta is 1, 2, or 4, and A is an integer, that realizes the complex, either the real complex or quaternion case, or the full Visscher or Lagarde type ensembles. Okay, does this setting make sense? Right? So this is a a two-parameter family of laws on points, which generalize the classical sample covariance matrices, and this is a matrix model for them. Okay. So again, what we want to do is we want to think about what is the operator limit of this W. Yeah, and of course it's going to be different than Tracy-Widom or stochastic array. And I'll just cut to the chase and give you the theorem. All right. So this is a theorem of Jose Ramirez and I from a couple years after the soft edge paper. So for any beta positive, any A bigger than -1, bring in another standard Brownian motion B, and here's your hard edge operator, okay? Second derivative minus first derivative with a shifted white noise convection term. So instead of a random Schrodinger operator, you get like a random diffusion operator. And then the whole thing is blown up by an e to the x, all right? So I don't know if there are any probabilists in the audience, but if there are, right, you view this thing as the generator for, this operator is a generator for a random process. It's Brownian motion. The generator for Brownian motion is Laplacian. It's Brownian motion with drift. That's white noise. And this means you take that process and you put it on a time scale change. All right? So there's a purely probabilistic interpretation of this object. All right? Now again, just like stochastic area, it acts on the positive half line and has Dirichlet conditions at the origin. All right? So if you build that operator, which, at this point, much like stochastic area, you should be thinking, how do I know this thing exists? Because I have this white noise in front of the derivative, and that somehow looks even worse than a white noise potential. But it'll actually be better, even though it looks worse to start. So here's the deal. So you define this thing, if it really is well defined, it has discrete spectrum, called lambda not lambda. Oops, that should be a capital lambda, right? And these are all non-negative. And if I take the little lambdas are the points under this general beta A ensemble, and I blow them up by n squared, take any finite k of them, any finite number of them, and these converge jointly in law to the ordered eigenvalues of this random operator. All right, so this holds for all beta and all A. Okay, any questions? All right, so I want to spend a few, so what's nice about this hard edge operator is that you can write it umpteen different ways, right? And each one is kind of nicer than the next. Okay, so I like to write this thing as having the negative of the generator of a Brownian motion with white noise drift, because I think it sounds fancy. But you can wash that all under the carpet and make it a much more tame beast. So the way to do that, or the classical way to do that, is to rewrite so that this object in the following way. Okay, it's a second order operator, so derivative times some function, another derivative, another function. And those functions, this S and M, are just simple geometric Brownian motions. So I integrate up once. I view it as a random potential, yeah?
So I have a question. So the right diagonal form of the matrix suggests the form of the operator.
Yeah.
But how do you fix or understand what is the boundary condition?
Yeah, right. I mean,
Even yesterday, how do you find it?
how do I find the boundary condition? Well, I mean, okay. In the stochastic area case, it really comes out of looking at the when you look at that variational principle we looked at in the discrete case, right? What you wind up proving is some smoothness, of the eigenvector, right? As it converges to a smooth function that's the eigenfunction, the corresponding eigenfunction for stochastic area, yeah. And if you think, I mean, in a silly way, right? You have an eigenvector for your matrix, and there's V1, there's V2, V3, and these are going to go to some functional values. But there's V0 equals 0 is there when you kind of complete the form if you want to write down the three-term recursion, right? And if the thing is smooth, right, you're not going to see any jump at 0. So you're going to naturally act on functions that vanish at the origin. I don't know if that's very satisfying. For this guy, we're going to see it in a very concrete way. And let's go through this, and then for the hard edge, it just pops up in a much clearer way that you have what the boundary condition is 0 is. So because what we're going to do is we're going to get an integral operator. So when you look at get an integral operator, the boundary condition is just encoded in the kernel of the integral operator. So maybe that'll help. All right. So, but you can instead of thinking about it as having a white noise coefficient in front of the derivative, you can write it in terms of potentials. Okay. All right, with two different geometric Brownian motions, and these are wonderful continuous functions M and S. And then wrong button. You can rewrite the second order operator as a system. Okay, so you rewrite the eigenvalue problem as follows. So I mean, this was probably hard to track in real time, but I promise you this is an equivalent formulation of the eigenvalue problem for minus tau. All right? So you write it as a system F and G, where F and G, again, if you want Dirichlet boundary conditions that I haven't explained yet, will satisfy this at 0. And then you can show that you can solve for G being this object as a once differentiable function. What I'm trying to I'm maybe not really trying to convince you, I'm just like throwing some things on a slide, but I promise you can view this tau as a classical Sturm-Liouville operator when you write it as a system. And all the coefficients are continuous, almost surely continuous to Brownian motions, but there's no white noise in the coefficients anymore. You can make that go away. What's better, and starts to get at answering your question, how we really prove anything about this, is that this tau has an explicit inverse. All right? And here it is. So maybe I should write these guys out. So do I have them here, maybe? Oops, no. I snuck ahead to my question. So I'm going to put these on the board. They'll show up a lot. So there are these functions Sx is either the ax plus, no, this comes with minus signs, 2 on square root of beta, b, no, this comes with plus signs, I apologize. Bx, and mx equals e to the minus a plus 1 x minus, the same Brownian motion, the same scaled Brownian motion. All right. So this is a completely valid formula for the inverse of tau. All right. Okay, so it's a random integral operator. This is in which you can prove that it's non-negative and compact on L2 of this random measure. All right. And in fact, using properties of Brownian motion, it's very easy to check that it's in fact trace class. Okay. So with probability 1, this integral is finite. All right. This is almost nothing, which means that it has discrete spectrum. Right? Okay. Also, if you think of what you can do is you can kind of decompose this. So this random trace class operator is actually product Hilbert-Schmidt. So if you play around, you can rewrite tau inverse, this random kernel operator, as coming in these two pieces. All right, as kappa kappa transpose, or here's kappa. And again, these are just formulas I'm flashing on the board, but it's another very easy exercise to show that this object is almost surely Hilbert-Schmidt. Okay? And so these things are just defined in terms of a simple one-dimensional Brownian motion. And now I can answer your question. So if you believe that instead of, this is what we're going to do, we're going to bypass the differential form of the hard edge operator, and we're going to show convergence at the level of the inverses. And if I prove, when I take the matrix model and actually look at the operator given by its inverse, and if I prove that it goes in some operator sense to this object, right? What is this, if I want the eigenvalue problem for this, right? I would need to look at this object acting on x, which is this, equals some constant lambda f of x, right? Now put x equals 0, right? The kernel vanishes at 0. So that's the Dirichlet eigenvalue here. Do you see that? So just because the kernel vanishes at 0, it's sitting there. And the advantage of having an integral operator is you just say, I just look for spectrum in L2, right? You don't specify the boundary condition. It's just built in. All right. And then, I mentioned all this not just because to convince you that the inverse is nice, but as I just kind of alluded to, this is actually how we prove it. If you remember, the matrix model has this form, right? The matrix model comes as a product of bidiagonals. It comes as something times something transpose, right? And that something is even easier than a tridiagonal. It's a bidiagonal. And so the game is actually to look at an operator limit of the rescale. Because remember what you have to look at is you have to look at you have to blow up w by n squared, right? You have to take the minimal eigenvalue and blow it up by n squared, which means you have to take w and blow it up by n squared. And at that level, you would see a differential operator, right? So you feed the n squared, one on each copy of your b, and we want to find an integral operator limit of n times b. It's inverse, all right? That's the game. And what's happening here is that the integral operator limit of this random bidiagonal matrix should be this guy. Okay? All right. Okay, so here's how to proceed. So this is just a bunch of linear algebra that's very simple to check. All right, so these are almost silly statements, but here's what you do, right? So any n by n matrix can be embedded into L2. Thinking of it as an integral operator with discrete kernel, right? And you just do this, right? If you want to think of your n by n matrix acting on a function in L2, you write it this way. And this is an embedding that doesn't change the spectrum, all right? Fine. Mm-hmm. And now if you play this game, what do we want? We want to play this game with the inverse of that bidiagonal matrix. You can compute the inverse of an upper bidiagonal, right? And it's an upper triangular matrix. And the inversion formula is super explicit, right? So that's a nice exercise if you want it. And this is actually what you get. So what I'm writing here, this little k sub n of x and y, this is the inverse of NB, right, the rescaled bidiagonal matrix, interpreted in this way. All right? So you can view this as, again, an integral operator with a discrete kernel, and here's your discrete kernel, right? It's a scaled chi variable over times a product of chi's, acting on, and this indicator just encodes the discretization, right? So it's going to be an upper triangular matrix because B is upper bidiagonal. And so you act on coordinates, x is less than y, and x has to lie in a little block. And I didn't tell you what xi and yi are, but xi and yi you can imagine are I over n. You're discretizing on level 1 over n. All right? Does this make sense? So you can convince yourself of all this as an exercise. So I just explicitly write out the inverse of the bidiagonal matrix model, and I embed this in L2 in this completely concrete way. Right? So it's a random integral operator with a discrete kernel. So let's rewrite that kernel in a little more kind of streamlined fashion. So when I write these brackets, it just means I take the integer part. All right? So again, I'm just reproducing everything and being a little fast and loose. This isn't exactly right? If you really look at what the indices do, but it's morally correct, right? And I don't know if I did this before, but I stuck a tilde on one family of chi's to drive home the point that this is the family of chi's that come from the off diagonal. So these two families of chi's are independent. So all the variables you see showing up in this kernel are independent. So it's really not a complicated object at all. I mean, the most complicated object is this, and that's a sum of independent random variables, right? Which is not complicated. So what you can show, I mean, this is very straightforward. For any fixed x, that this first bit converges to 1 over the square root of 1 minus x, and this sum, right, now I'm starting it off at just a fixed point, up to nx, the sum of logs of ratios of chi's converges to a normal with explicit mean invariance, right? It's an easy exercise, okay. And then at a process level, right, so that's just, it's an easy exercise just to prove this for a fixed x, but then there's a process level version of it. And the process level version of it, it tells you that your limiting kernel, bidiagonal kernel, or the limit of those bidiagonal kernels should be this thing. Okay, it's somewhat ugly. And B is a Brownian motion. That's encoding the normal here. Right. So there's your random, half of your random integral operator. Okay. So it's not pretty to look at in this form. And it's worse still if you put it all together, right? Because this is just half of the operator, right? You have to take this thing times its transpose. So you write that out, and that's the thing, okay? So you put it all together, you get this, but remember this is acting on L2 of 0, 1. Yeah? And the operator I advertised at the beginning of the talk acts on L2 of the half line with this random measure. Okay? But this would be the target limit. Okay? So this is a kernel on all x and y living in 0, 1. Right? And it's random through this Brownian motion. And here's just how to get back to the thing that I advertised to you. You just change variables. Right? So here you take this formula, and you change variables to pull the thing onto the whole line. Okay, so you use this in conjunction with Brownian time change, and you can rewrite this mess after a change of variables as this object. Now on L2 of 0 infinity, remember this is your S and M, these geometric Brownian motions. It's just, yes?
The first formula is also true for the gamma greater than 1.
The gamma, the alpha or the?
So in the case of the
This thing. Well, no, I mean, you're in a different, so what do you mean by the first formula?
So you said that you just took the inverse of it.
Oh, absolutely, absolutely. I see what you're saying, yeah. Right. So yeah, but that, it's true, right? I mean, the inversion formula is true, but the thing is there, when you're in this, this leads to a problem I thought about a lot, right? Because what happens at the lower edge for general Laguerre-Visscher type matrices when you scale kind of around the soft hard transition is even not settled fully for beta equals 2. So you can do this kind of inverse business, right? But the deal is when you're here, you have to center the thing, right? So it's not fair, you know what I mean? So it's not fair to invert and then center. You should really center and then invert. Once you center, you know what, you lose the BB transpose structure. You can certainly invert it, right? But you won't be looking in at the right place. Does that make sense, what I'm saying?
And here in the chamber variables, you are using in the chamber variables,
Yeah.
these chamber variables gives this formula only for these.
Yeah. I mean, this is at the limit, and this is just, I mean, I advertise in this, the only point I'm making here is that you naturally, the discrete operator, the matrix model, when you embed, it naturally lives on L2 of 0, 1, but then the limiting object is ugly, and it's just nice to put it on the whole line. It's just a prettier formula, right, to think about and look at and understand. So I'm just saying this is what you get when you just follow through, and to get what I advertised at the beginning is just a simple change of variable that doesn't change the spectrum, right, of the integral operator. Okay, and this is written in this symmetric form, but remember the kernel I had was this object just times m. So you instead of thinking about it on L2 of 0 infinity, you resymmetrize so you're on L2 0 m. And the reason I do that is, again, I mean, this is a little bit of a cultural aside. If you know something about diffusion theory, the S is the scale function for the underlying process, and the m is the quote-unquote speed measure, and the speed measure is the invariant measure for the diffusion tied to this operator. So it's just natural, if you come from a certain place, to want to write the thing symmetric in terms of its speed measure or invariant measure. That's what's going on, and that's why I prefer to write it in this form, okay? Instead of being symmetric in L2, flat L2, symmetric in L2 of this m measure. All right? So but here, what do we actually prove? Okay, so let me just give you an actual statement. So again, so now you have kind of everything on one slide. Here in the first line, the first display is this ugly form of the integral operator for the B, for just the bidiagonal, the inverse bidiagonal in L2 of 0, 1, right? Here is our, kind of streamlined version, right? This K sub n, remember, is our streamlined version of the random kernel, again, acting in L2 of 0, 1, right? Unlike the soft edge, the embedding here, there's no mystery, right? It's an integral, they're both, for all n, it's an integral operator.
So to the K beta A in the first line is well defined trajectory by trajectory.
Absolutely. And it's even almost surely Hilbert-Schmidt. You can check that just by some properties of how Brownian motion acts at infinity. Right? Okay. And now this, here's your discrete kernel, right? So here's the statement, okay? You take any sequence of operators, right? What's capital K sub n? Well, it's the L2 operator on 0, 1 corresponding to this random kernel. So, you give me any sequence of these operators, I can find a subsequence such that this holds, and a probability space. What does this say? This says I have almost sure convergence in Hilbert-Schmidt norm. Okay? So when you put that together with the other half, I'm proving that over subsequences, I have almost sure convergence in trace norm. And then all the spectrum just goes over. Right? There's no arguing lambda eigenvalue by eigenvalue like there is in the soft edge, right? Because you have these compact integral operators you're dealing with. So this is basically all you need to add to what I've told you. The simple central limit theorem, understanding the pointwise convergence of this object to this object, is a little bit of control at 1. Because if you stare at this thing, you get some singularities when x and y approach 1, right? So you just need a little bit of integrability of these objects. And that's really kind of reworking the law of the iterated logarithm for this family of chi-random variables. That's as hard as it gets. Okay? Okay, so I know it's a lot of formulas, but it's really a pretty tame object. So the probability is really wonderful for proving convergence, but as we've seen, it's not so great for getting formulas, right? And I know this is like a formula-heavy crowd. So I want to give you, here's a little comment that shows how frustrating this can be. So here is a little fact. So let's go back to the beta Laguerre density. All right, here it is. Forget about random operators. Certain magical things happen for very special betas and a's. Right? So let's take this combination of beta and a. Beta and 2, a plus 1 equals 1. For example, this takes place when beta equals 2 and a equals 0. So in the complex case, if you remember back to what these random matrix models look like in the full matrix model case, that's the complex Gaussian case when the matrix, right, M, we formed MM transpose, M is completely square, right? A equals 0, there's no difference in dimensions. It's a square Laguerre ensemble. Okay, so let's say I want to find the limit law for the minimal eigenvalue. Well, what do I got to do? I got to integrate this density over, if I want the minimal eigenvalue to be bigger than t, all the eigenvalues need to be bigger than t, all right? If you remember that, so what's going on here? What's special about this choice? What's special about this choice is this dopey little polynomial part of the weight vanishes, right? That's what's special, okay? Okay, so I need to do this integral. Well, why don't I shift all the eigenvalues by t? So I tell you, I want to just change variables in each eigenvalue coordinate to get t back to 0. This doesn't change the van der Maan. It doesn't matter if it's van der Maan to the 43rd power, right? You just shift all the eigenvalues by t. You still get the van der Maan. The rest of the way is just exponential. So you just shift out the exponential, and you get this. This is an equality, right? So in fact, for the general beta A, hard edge law, when beta and A are related in this way, it's just an exponential, right? The limit law is just, all this Pan-Lavey junk is just an exponential, okay? And in fact, it's an exponential for all n. There's no limit, right? For all n, it's an exponential random variable. So what does this mean for my favorite random integral operator? It means the following. This is a true fact that I can't prove, okay? So here is a characterization of the minimal eigenvalue for my general beta A hard edge operator when beta and A satisfy this. Where does this come from? This is the Dirichlet form for the differential version of the operator, because here is your m, your invariant measure, but when you stick in a plus 1 equals 2 on beta. So if I solve this random variational principle, it has to be an exponential random variable.
So, excuse me, I'm confused with the notation.
Yeah.
Just in the second line, why do you have the second equality? No, sorry, the second display.
This one?
No, the second line.
This one? Oh, how do I get it? Okay. So change all the lambda I into what? Lambda I plus t. Let's do it. You'll need some paper. No, you don't need some paper. So you see, I make a change of variables. All the lambda, you see it? Yeah. And that doesn't work for any other betas and a's, because when any other betas and a's, you have this thing, and then it's a mess. So
it's
right?
self-similarities.
Yeah, it's just, it means like at the level of eigenvalue densities, in this special case, it's a triviality, right? So this is a strange one parameter, there's two parameters, but then when they satisfy a relationship, this possibly exotic law is just an exponential, right? But this means the following, right? About, I have this little quadratic form in terms of a geometric Brownian motion. I have to minimize this thing over, non-zero functions who vanish at the origin. And then this object has to have an exponential distribution. And if anyone in the audience knows things about the Dufresne identity, made popular by Matsumoto and Yor, they wrote about 20 papers about these magical identities of geometric Brownian motion in the early 2000s. It looks an awful lot like this. But I tried very hard to prove this. And it wouldn't be that exciting because it's true. But I can't prove this directly from Brownian motion. Okay, so the probability has some drawbacks. Okay, on the other hand, when did I start? Does anyone know how much time I got? Does anyone know when I started? Because I don't.
So you have 15 minutes.
I have 15 minutes. I'm going to end early. It's wonderful. Okay, I think everybody will be happy. Okay, so there is a Riccati description at the hard edge. And this, what I do want to show you is that one thing the probability is good for, again, it's good for limit theorems, so I'll give you a proof that for all beta, you have this soft to hard transition, right? So that all these limit laws really, converge back. All these hard edge operators really encode the spectrum of the stochastic array, which of course gives us this general beta Tracy-Widom business. All right. For this, we need to bring in this kind of Riccati diffusion description for the hard edge operator. All right. So what I'm going to do now, where are you, button? There we are. Okay, I'm going to rewrite the eigenvalue problem for the hard edge via the integral operator. What I'm doing for you here is I'm writing this out, right? Okay, so this is what the eigenvalue problem looks like at the level of the integral operator. And here and now I'm answering your question, right? From here you can read off that if you want this to be satisfied, when you put t equals 0, you get 0 on the right-hand side, and there's your Dirichlet condition. All right, anyhow, Brownian motion is continuous, so you can argue that the right-hand side is actually smooth in t, right? Has one derivative in t, and so any eigenfunction has to, all right? So you can take a derivative through this thing. And when you take a derivative through this thing, what's going to happen is you're going to free up an instance of this geometric Brownian motion, right? One of these kind of objects is going to come out. You won't be able to take another derivative, because if you try to take another derivative, you have a derivative of e to the Brownian motion that has no derivative, right? So you're already proving, just from this, staring at this integral operator, that the eigenfunctions for the hard edge operator are C3/2, right? They have one derivative with that's Holder continuous 1/2, because the derivative of the eigenfunction has to inherit the regularity of Brownian motion. Okay, you just see that from looking at this thing. Okay, so you can take one derivative, then you're stuck, but then you can take an Ito differential through. All right, so if you do those two things, here's what you get. So you take one derivative, you get this system, then you take an Ito differential through, and you write this all in differential form, you get this system. All right? Where psi is like your target shooting eigenfunction, right, for fixed lambda. Remember the Riccati trick? The Riccati trick is we need to look at the log derivative of this psi, right? Psi prime over psi. And if your psi solves this system, Q solves the following SDE, all right? And if you, maybe I should write, it's uglier than the, for the soft, is there, here are the erasers. It'll appear on a subsequent slide, but maybe it's nice to look at here. Remember, for the soft edge, for stochastic area, the Riccati equation, I called it P, was 2 square root of beta d bt plus lambda plus t minus pt squared dt. Okay? And tracking explosions, certain explosions of this object, tracked the stochastic area eigenvalues. The explosions of this gave you the counting function for stochastic area. So the statement that I'm gonna make formal on the next slide is tracking explosions of this Q, which admittedly is much uglier than this, right? And it depends on a couple of parameters, depends on A and beta. This gives you the counting function of the hard edge eigenvalues, right? So again, it's going to be passages of this thing starting at infinity because of the Dirichlet eigenvalue. Right? Okay, so here's the statement. Okay, so let's take, you think of the law induced on continuous paths by this process, started at infinity, and like before, restarted at infinity after any passage to minus infinity. The presence of this minus q squared still means that you can get down to negative infinity in finite time. All right? The other thing you want to keep in mind is that what's cute here, think about lambda being 0, because the eigenvalues of the hard edge operator are positive, right? So if I wanted to compute the probability the ground state eigenvalue of the hard edge operator is bigger than 0, I better get 1. So this means that this dude should not explode if you put in lambda equals 0. If you put in lambda equals 0, right? Everything has a Q in front of it, right? So this object will get stuck at the origin. This thing can never get to 0 even, let alone minus infinity when lambda equals 0, right? So if you get near 0, you need this to push you over the edge, right? To push you into the negatives. And as time goes on, you get less and less push. So just like this SDE, qualitatively, the longer the process lives, the more chance it has to survive, right? The longer you live. That's not how it usually works, right? But the longer you live, the more you live, right? So here's the statement. Here's actually what it looks like, all right? So these capital lambdas are the ordered eigenvalues for the hard edge operator. So I want to compute the probability the ground state of the hard edge operator is bigger than lambda. And there's a little weird thing that happens. It's like I lied to you. What I do is I take this diffusion Q, I started off at infinity at time 0, and I ask that it never hits 0. And if I want to know I did it again. This should be a capital lambda. The kth biggest eigenvalue of the stochastic area operator is less than lambda is that I hit 0 at least k plus 1 times. So I'm tracking passages to 0 instead of passages to minus infinity, all right, like we had before. Here's the deal. If a is non-negative, you can replace this with hits to minus infinity. So if you stare at that integral operator, getting back to your question, it actually has a Neumann condition at infinity, okay, for all a. But for a positive, you can use Neumann or Dirichlet at infinity because the process just doesn't see infinity. Okay, so there is if you know this language, there's a limit circle versus limit point, kind of criteria for this operator at infinity. And for a negative, which only means a between -1 and 0, you have to take Neumann at infinity. But for a positive, you can take either Dirichlet or Neumann at infinity. That's just the deal. In fact, we screwed this up in the original version of the paper. We just didn't notice the subtlety. We reported that it was always Dirichlet, but for negative a, you have to be more careful. So it's a little tricky to see the level of operators, but if you know some diffusion theory, what's cute, you can check. And when a is non-negative, this process Q, it will hit minus infinity with probability 1 once it hits 0, right? So that's the way to see at the level of Riccati that hits to 0 and hits to minus infinity are equivalent. Right? At the level of operators in the counting function, you have to do more, okay? So again, we have some diffusion, and we can count passages to, we can count certain passages, and that gives us the counting function for the hard edge operator. All right. So here I just want to give you the proof to give you some idea of how you can prove that all these hard edge eigenvalues, when you take a to infinity, get you back stochastic area eigenvalues. All right. It would be lovely to do this at the level of operators. That's another open question. I haven't been able to. So you should be able to take this hard edge operator, maybe in differential form, in its appropriate version, and show that it homogenizes to stochastic area. That appears tricky, but we can do this at the level of Riccati. Okay, so here's what we do. So here's the theorem. Sorry.
How is it possible? How is it possible that it's difficult on the level of operators and possible on the level of Riccati?
Well, I mean, so here you know why it's okay. With the level of operators, you've got to prove something. Again, I mean, on one hand, the operators, sometimes have some advantage, right? You prove things omega by omega, right? Just on the operators. You got to make some hard estimates that are true, like almost surely. At the level of Riccati, you just have to prove something about the distributions. You're going to prove a much weaker statement, right? You're going to prove convergence and distribution, right? So you just have to make some, rough estimates on what this diffusion looks like. I don't know if that helps, right? When you use Riccati, you're going to compute things in law. And the level of operator, you're got to show convergence and operators. And that's why. So here's a little statement. So if you take the ground state for the stochastic, now call it stochastic Bessel operator, if you shift the parameter a just to make these constants come out cleaner, so here it is. If you subtract it off by a squared, divide by a to the 4/3, for all beta, this converges to Tracy-Widom beta in distribution. Okay. So here's what you got to do, and here again is our friend from last time. Remember, Tracy-Widom, the distribution function for Tracy-Widom beta is the probability that this diffusion never hits minus infinity. And for all a positive, and I'm going to take a bigger than 0, a huge, so a is bigger than 0, this probability, right, the probability of the ground state for the hard edge operator being bigger than some mu is the probability that this diffusion never hits minus infinity. There's two diffusions, and I want to show that the probability is that each of them don't hit minus infinity to line up. That's what you have to show, and that's why it's an easier tool to work with. Okay, so what can you do? Well, the idea is, why don't I put all these scalings in and just show that these diffusions look the same, right? What we're actually going to prove is that these two diffusions induce laws on paths, and if I show that under this scaling, these two diffusions induce the same laws on paths, right, in the limit, then their hitting distribution should be the same. Okay. So this is the scaling. When I do this hard edge diffusion, right? at, with parameter 2a and spectral parameter mu, if I put the spectral parameter equal to this object, which is how I scale the eigenvalue, I want to show this converges to the soft edge diffusion. Okay? And so the next slide will be ugly, but it'll just to show you how you can do it. Okay? So what's the idea? The advantage is you know what you want, right? So I want to show this process for which I have an explicit SDE looks like that process. Okay? So you just you know where you're going, so you just have to find the right change of variables. Okay? So here's what you do. So this is this Q with these weird parameters. Here it is again. I make this change of variables that might seem to come out of nowhere, but it's engineered to get what I want, right? Now this new process, all right, certainly if Q starts at infinity, eta starts at infinity, right? And if Q hits minus infinity, eta hits minus infinity. So tracking explosions of this rescale Q is the same thing, the same event as tracking explosions of Q. And now you just feed this junk through, all right? I mean this is ugly, as I advertised, right? But I have an explicit equation for Q, I have an explicit equation for eta. Here it is. Here is this bloody mess, right? But now think about what happens. A is going to infinity, right? So for short times, for finite, compact sets in time and space, for compact sets in t and eta, what happens to this thing? Right? Well, that looks like 1. Boop, boop. What does this look like for compact time? Right? E to the minus blah blah blah. This stinks. There should be a minus 2/3 here. That goes to 0 because the minus is in the wrong place. It's either the minus a 2/3. That goes to 1 and you get the lambda. Right? The right exponent is here. There should be a minus 2/3 there too. This goes away, right, and gives you t. Here's your eta squared, right? That nothing happens there. It goes over here, and now this junk all goes away. And this is what it looks like, at least locally. And there's your soft edge diffusion, right? So obviously there are things to prove, right? But that's just the idea. And if you know where you're going, you can engineer the right change of variables, and you can push through that this equation for Q, at least after properly rescaled, looks like your equation for P. And there's no Bessel, and there's no Painlevé 5 or 3 to 2, right? It's just some coefficients of random ODEs, and that's where the transition comes from. Okay. Hopefully I still finished early. No. Oh, okay. Okay, I'm done. Thanks.
Questions?
Yeah.
So in the case of areas, when we discuss the Gaussian,
Mm-hmm.
When you discuss the Riccati equation, you draw a picture with the parabola.
Yeah.
Can you do the same for the Bessel? And can you see if from the picture, if you go to Airy and the transition at a plus 1 equal to 2 over beta? What happened in the picture?
Yeah. I mean, let's go back to this not so ugly form, right? Right. Here's the here's the way maybe this is the mantra, right, for this transition. Maybe this is a better way to see this. Think about A being huge, right? Pre-scaling mu, okay? So if A is huge, okay, what's going to happen? What's going to happen is, well, okay, even if A is getting big, it can't beat this at first, right? So you start off at infinity, this is going to come down lickety-split to where these two things balance, right? So we're, roughly A times Q equals Q, okay? And then, what was the scaling with the mu to make this stick, right? Now you got to pick what mu should be to make this all, even if you want to find some transition, you're trying to find where all these different things, these passively competing things balance, right? To first order, mu looks like A squared, all right? And then if you have an A, Q squared, and roughly A, and then you have an A squared, e to the minus t, but this is all happening for incredibly short times, right? So it's like this e to the minus t isn't there. And then you complete the square here. You see what I'm saying? You're going to complete the square, and you're going to get A minus Q squared. And there's your parabola. Does that make any sense at all? Yeah, I mean, so on a very short scale, right, this thing is really looking quadratic, but centered around A, right? And then when you look at local coordinates there, you see the parabola. Go.
And when A, in the other case, the funny case, when A plus 1 is equal to 2 over beta, then in that case, so does it correspond to the probability of
well, it's the same.
never hit, so to be exponential, right?
It would still be exponential. I mean, I can't see it from here. I mean, the only thing I see, and that's nice in all this picture, is when this is the invariant measure for the underlying diffusion.
Yes.
In that case, when A plus 1 equals 2 over beta, right? This is a martingale. That's the only, I mean, I know that sounds ridiculous, but that's the only kind of, if I want to think of something like that looks good probabilistically, that's the only thing. I don't see anything good from here. I don't see anything special there. So, yeah.